Question 11. Consider the function fx is equal to x squared minus 3 over x, where x can't equal 0. And part A asks us to find f dash x, or the first derivative of fx. Okay, so for this, you're going to need to know how to differentiate a function. And actually, specifically for this one, you're going to need to know some of your indices laws. Okay, so specifically, how can we rewrite 3 over x so that it's easier to differentiate? All right, now the way we're going to do that, okay, is write fx is equal to x squared minus 3x to the power of negative 1. Okay, so the indices law that I use there is essentially when you raise any number to the power of, let's say if we go 2 to the power of negative 1, this is equal to 1/2, right? Equally, if we had, let's say, 2 to the power of negative 2, that's equal to 1/2 squared, which is equal to 1/4. Right? So whenever you raise a power to, a number to a negative power, it's essentially moving it to the denominator. All right, so I've done the reverse here. I've taken the x from the denominator, lobbed it up to the top, to the numerator, or to the top line, and I've just represented it as to the power of negative 1, right? And so now I can quite easily apply our differentiation rules. Now, this is in your formula booklet, how to differentiate. So I'll write that here. If we have fx is equal to, let's say, ax to the power of n, okay, then the first derivative of this function here, okay, is going to be equal to, we bring the power, so n, to the front of the equation and multiply that by the coefficient, which in this example is a. So we're going to get n multiplied by a, right? Then x, and then we have to subtract 1 off the power. Okay, so you can kind of think of it as 2 steps. You bring the power to the front and multiplying the coefficient by that power, right? So that's the first step. And then the second step is to remember to subtract 1 off of the power. Okay, so if I apply that to our original function here, we have got, and so I should note that you do this to every term along the function. Okay, so this, the function could be lots of terms, a long polynomial, and you apply this rule to each term of the function. All right, so for this one, I'm going to bring the 2, the square, the power of 2, to the front and multiply that by the coefficient of x, which in this example is just 1. You don't usually write a 1 there, but the coefficient of x is 1. So we're going to get 2x, and then I have to subtract 1 off of the power. Okay, this is another example where we don't write x to the power of 1, we just write x, and that means it's to the power of 1. Okay, so x squared, when we differentiate x squared, that becomes 2x. Right, and then now we move on to the next one. Right, so we're going to get let's do everything. So we're going to go minus, and then now this is going to be, have to bring the minus 1, so the power to the front. All right, and that's going to have to multiply 3x, and then we're going to have to go minus 1 minus 1. Okay, so we still have to subtract 1 off the power. And if we clean this up, let's write that back in. We're going to get 2x, okay, plus 3, and then 3x to the power of negative 2, okay, which we could write if we wanted to follow the format in the question. We can say 2x plus 3 over x squared. All right, and so there is the answer to part A. So part B says, line L is a tangent to fx at the point 1, negative 2. Use your answer to part A to find the gradient of L. Okay, so another term you can use for the first derivative is, you can call it the gradient function. Okay, it's quite a good thing to remember the link between a function and its first derivative. Okay, so basically what the first derivative does is it will tell you the gradient of that function at any particular x value that you substitute into the first derivative. Okay, so for this question here, we're told that we need to find the gradient of L. Okay, and we know that L is a tangent to the curve at this point here, where x is equal to 1, and obviously y is equal to -2, but that's not so important at the moment, just when x is equal to 1. All right, so then to answer this, what we need to do is sub x is equal to 1 into f dash x, or our first derivative. All right, and that will look a little bit like this. So we'll go f dash x, sorry, we should put 1 in there, is equal to 2 times by 1 plus 3 divided by 1 squared, which is just 1. And so that's 2 plus 3, which is equal to 5. Okay, and so now we can conclude that the gradient of our line L is going to be, what have I done? Is going to be equal to 5. All right, and there is the answer to part B. Okay, cool. And so moving on to part C, we are asked to determine the number of lines parallel to L that are tangent to fx and justify our answer. Okay, so this one's definitely a step up from the other two, right? So essentially what this question is asking us is to find how many possible values of x are there for which you sub into f dash x, or our first derivative, and then that equals 5. So that was a bit of a roundabout way of saying it, but yeah, we need to find the possible values of x where find x values for f dash x is equal to 5. And essentially this is saying how many times does our function here have a gradient of 5, okay, but not including the line L. Okay, so we just need to find how many lines that would be, the number of lines that would be parallel to L, aka have the same gradient of 5. Okay, so the best way to do this is to graph these on our calculator. Okay, and I'm going to bring you over to a online I'm going to bring you over to TZ2 so you can hopefully see everything a little bit better, visually see it. Yeah. Okay, so here is TZ2, it's a graphing calculator. Now I'm going to write in our first, so just fx. Okay, so fx was equal to x squared minus 3 over x. All right, and so there is our original function fx. All right, then our first derivative that we calculated, okay, is 2x minus 3 over x squared. Right, and then now it'll be hard to see, but here this represents, sorry, I beg your pardon, that should be plus 3 over x squared, plus 3 over x squared. And so here, what you can see with our blue line, the blue line is representing the gradient of the red line. So the easiest bit to see here is that at this point here, this minimum, that is when the gradient of our red line is equal to 0. Okay, and that is represented by the blue line here crossing the x-axis, so being equal to 0. You can see how their x values are the same. All right, so that's a good way to visualize that the first derivative is the gradient function and gives you the gradient of the original function, if you will. Okay, and so we're asked to find essentially when our first derivative, so f dash x, the blue line, is equal to 5. Now, the easiest way to do this, I'm going to get rid of our original function, okay, because we don't need that anymore. We're just going to put y, and put a horizontal line at y is equal to 5, okay? And here we can see each time our first derivative is equal to 5, or the gradient of our original function, fx, has a gradient of 5. And this one here, this 1, 5, this is representing the when you're representing the line L, which is tangent at when x is equal to 1 and then y is equal to -2. If we, I know that says there, it's y equals to 5. Let me bring back in, let's bring back in our original one as well. And so you can see that. Okay, so here you can see this is 1, 5, all right? And then if we look at now it's the purple line I see, but at 1, 2, 1, -2, sorry. So that's that point there, okay? And so line L is tangent here and has a gradient of 5, all right? Let's get rid of our original function now, so we don't really need that. And so to answer part C, there are 2 other points of the graph fx, which are parallel to the line L. All right, so we've got 2 points here. And so that is the answer. Let's bring you back over to pad. And so we will conclude that there are, so let's go into green. So f dash x equals 5 has 3 solutions. And so therefore, there are 2 lines. We'll just say 2 lines. That is the answer. Okay, so not including line L. So 2 lines are parallel to line L. And there is the answer to question 11.